So thank you very much, and it's a pleasure to be here and talk about some efforts. So I'm coming from the application side and want to give you some perspective how we are approaching CFD solvers and finite element methods in general. So what I'm going to concentrate on, so I start with some of the application areas. So I'm kind of from the theoretical mechanical engineering. So CFD is one of the big consumers of computing powers on the supercomputers, and kind of the things that we're interested in is flow at high Reynolds numbers, and high Reynolds numbers means you need high resolutions because you have fine structures that you need to resolve, and there is, especially in the transient parts of simulations like airplane takeoff and landing or automobile simulations, that you cannot rely on statistics, but you really need to collect them on your own. So you need a lot of degrees of freedom, and something that I want to be able to do is like geometric flexibility, of course HPC, and the method we choose is high-order finite element and discontinuous algorithm because just they are able to do that. And what our selection was when we started writing a new code 5 years ago was that we kind of wanted to start a new code which is kind of targeting applications in CFD and in biomedical applications, but we want to rely on existing mathematical frameworks, and that would be one of my contributions here. So just shortly, I mean, we look at Navier-Stokes equations, so it's kind of the general equations. We have meshes and on elements we have high-order polynomials. So in the end, that's kind of what we want to get out from the simulations. And what do we want to have from mathematics? So we want to be flexible in a sense, how do we time stepping? How do we choose the spatial discretization? So there might be different parts, and then in these equations, there's an interestingly large amount of development still in theory, in mathematics, in numerical methods. And kind of this feeds back into when you write a solver, because there is a lot of things going on. Of course, you need to be flexible. That's kind of the theme I want to focus on. And of course, the other thing is you want to be flexible because you want to couple multiphysics into different parts depending on the application. For example, in biomedical simulations, we've been doing simulations on the human lung, where you want to be able to couple some scalar transport, so oxygen, which gets into the lung, and carbon dioxide, which comes out, and there is this exchange. You have some sophisticated models there, so that's what you want to do. And in time stepping, of course, like just 2 examples here. This is kind of the splitting scheme where you split down the equations into similar parts. So this is high-order method, high-order splitting schemes. And the other one is a coupled one, and you have to balance what is giving the better performance. And spatial discretization, high-order finite element means we have polynomials, which we track over a domain on the elements, and the polynomials, they kind of matched by some particular forms. So we kind of end up with an equation system. It can be explicit, implicit. On this page, it does not really matter. What is important is there's a lot of integrals and a lot of operators mathematically that we need to be able to discretize. And as I said, I mean, like even we made some contributions. It's pretty fascinating how much, because people have been doing DG in various areas for 30 years, it was fascinating to us how many things which are still open. So that's something you need to be when you make a code. You need to be flexible. And one of the things that was open is that how you kind of stabilize high Reynolds number flows. In the compressible context, it's not so important. In incompressible, it turns out, like we wrote a series of papers, you really need to be able to change the formulations, and we rewrote a lot of things just because we learned something from the mathematical point of view. Okay, so that brings me to the main topic here is the software design. How do we approach this in terms of coding? How do we make this reusable, and how do we target the next generation of hardware? So kind of, I hope I convinced you that there is application and mathematics developments that we need to track. We need to be flexible, so we need to react and don't just rewrite the code again after a year when somebody writes a new paper about a new method. So that's something we need to do, and of course, like when you want to be efficient, you select the most efficient parameter depending on your setup. You might have a different mesh, and sometimes you might be able to use more high-order methods, which have fewer elements. Sometimes you need more elements in the mesh just to represent it. And the next point is that, of course, you have solvers, so iterative solvers for large systems. It's, of course, important that they are optimal complexity, because you imagine you have billions or tens or hundreds of billions of unknowns. Of course, you need an algorithm which scales as O to the n and not n to the 1.5 or 2, because that just kills you. And one of the examples is Multigrid. And then you need to select the most efficient implementation, and that's kind of the topic that I'm going to concentrate a bit more on in the next few slides. And the important part is, of course, the memory bandwidth, especially in simulations, so that's mostly the memory bandwidth limit that you're seeing. And the other thing is, of course, like when we have new architectures, we can select which kind of extensions are we using. And here on the right-hand side, I just have a picture where we just made some measurements of our code in terms of efficiency of the vector instruction. So watts per, or kind of application throughput, degrees of freedom processed per watt that we plot on the right-hand side here. And what you see is that, well, when you increase the level of the vectorization width, then we gain in terms of throughput. But so that's kind of course, one of the reasons why Intel was increasing it. So this is an Intel CPU on the same Xeon Skylake, but it really shows you that you can gain in efficiency when you do the vectorization in our code. And of course, then we have the architectures. We have Xeon Phis, we have GPUs, we have ARM CPUs, as we heard. So there's really a lot of things that we need to bring together. And so how do we approach this? So I'm kind of coming from the context where we have libraries to separate the concerns. So we have kind of the mathematical framework somewhere. We have parallelization libraries. So we go to MPI, of course, and then we separate the different things. And I'm coming from the DEAL2 library, which is a big finite element library. It has not been that much high performance, at least before I started working in the project. But we gained a lot of functionality just because we did not find it anywhere else. So that's why we included it. And the flow solver that we built on top of that, it's really something we try to have it compact. In a sense, now I just write some kind of approximate number of code, lines of code. So it's still it's quite surprising that we have 70,000 lines of code in the application code, which is a lot. And I was kind of shocked whenever we have this, but I guess that's just the number of lines of code that you produce in the end. It does not really depend on the framework. You always write as much as the programmer team that you have is able to build, right? That's kind of the number of lines of code. I mean, that's always something which depends on how much resources you have and not so much how capable the tools you're building upon are. So that's something we do, of course. Now when we go into it, like the DEAL2 library, it has 700,000 lines of code. We're using not all of them because, of course, it's a huge library which does many things. We use around 200,000 lines of code. The same thing like the Trilinus project, that's one of the solvers that we use for algebraic multigrid. The project as a whole has a few million lines of code. We don't use all of them, but again, it's a sizable fraction. Of course, if we want to rewrite everything, that's not going to scale, and we have to rewrite it again when you change architecture. That's not what we want to do. So, of course, that's what we do, and I'm just saying that while we try to separate the things like what goes into the CFD into the CFD code, well, it should be kind of the implementation of the equations, and of course, you need the control logic, like how you control the loop when you do output and things like that. And how you set up the examples, what parameters you choose. I mean, it adds up really quickly in CFD because you have parameters, you have meshes, and so on. But that's difficult enough. Whereas we really try to put as much of the mathematics as possible into a library. In our case, the DEAL2 library. We also have the kind of the backends for the hardware, like SIMD or CUDA. We have MPI parallelization, which then goes on to other libraries, depending for the meshing. We have bForest, which is a project for adaptive meshes in parallel. We go to Trilinus and Betsy when we do algebraic multigrid and some matrix-based things that are already there. And in general is that we start out quite often in the application code, and at some point we realize, well, this is a generic pattern, and then we move it to the library again. So of course, this is an interactive process as a whole. And it helps us also to maintain the code flexible in the sense that when we feed back, that's maybe something I should still say, the last topic here is when we feed back, it's also kind of separating, forcing us to have clear interfaces between the two, which is something which is more easy than to rewrite if you have to. So now the central algorithmic component that we do when we look at finite element algorithms and solving systems. Now think about Poisson equation. You do it with a high order finite element method. In general, you look into the profiles of the code, and in classical code, you see that you spend a large fraction of the time in matrix vector product. So iterative solvers with standard smoothers. And the standard approach in finite element method is you do sparse matrix vector product. Of course, when you come from finite differences, you will say, well, that's a stupid thing to do. You should do stencils. Now, think of it, it's unstructured mesh. We have deformed geometries. So that's kind of the finite element way of thinking it. Now, of course, the problem is that's severely memory bandwidth limited. If we think of matrix vector product, you get between 0.16 and 0.25 bytes, flops per byte, just in terms of the matrix entries, which scalars like, which give this ratio, and you cannot fit it in a cache. And this was bad in 2005. It's just much, much worse today. And it's not going to be better on the next generation of hardware. So this is really something you need to address, because hardware is like capable of doing up to 100 times the flop per byte ratio than this. So it's really something that we decided, well, it's around 2010, 11 that we decided, well, we need to go away from the memory transfer. And the only way to go away is that you go from matrix-based to matrix-free. So you cannot afford loading the matrix into CPU for just one application of the operator. So you really need to construct the matrix entries on the fly. And there is different way of doing it, like stencils coming from finite differences. There is people doing it in finite elements as well. It works with low order methods, and we have some structure in the mesh. If you go high order, the most appropriate way of doing this is integrals, and that's what I'm going to choose. And the interesting thing is that even here, like you see that the flop to byte ratio is now between 1 and 8. And it's a bigger ratio. I mean, I have some figures here on the right-hand side. You can select between different implementations. You can do more computations on the fly, or you can do more pre-computation and loading. And that's really something you want to select. And the interesting part is also, of course, that at this point, when you have 1 to 8 flops per byte, it's interesting in the sense that both the memory access is important and the arithmetic work. And we have a very strong relation, so this kind of library approach and what we're doing here, it's strongly related to what is the US exascale project are doing. In their case, it's the CEED, Center of Efficient Exascale Discretization, so it's the high order finite element approach in the US, and we're doing something similar in Germany. Okay, so just quickly, when we do matrix-free operator evaluation, so in classical finite elements, you say you assemble a matrix, and later you apply matrix vector in an iterative solver. And when you do matrix-free, in our case, it just means, well, I just pull in the assembly loops into vectors. So kind of I just apply the local operators on the elements on a vector. And these local operators, of course, are not formed by forming the local matrix either, but you just apply that by smart tools, and you write that into the vector. Of course, one thing which is important is that we want to have Velita locality to keep the arithmetic intensity. And we, of course, in the end, we don't care so much about what is the gigaflops per second or gigabytes per second. It's like similar to what we were hearing from the meteorological simulations of Thomas Schultes, that essentially we care about the throughput of the operator, and the other thing is just secondary. So just when you think about it, like how is a matrix vector product on an element level in finite element methods? Well, you can write it as an integral, and if you do it an integration, well, you can break it down as I write on the right-hand side here. Well, you can write it down as kind of a series of matrix times vector operation, like the S matrix is kind of an interpolation matrix from the nodal values of the polynomials into the derivatives in quadrature points. Then you have a quadrature point operation, that's the W, that's kind of where you put the physics. And then again, you do the summation over quadrature points and testing by all test functions, that's again an S transpose matrix. So that's kind of how you can break it down. And now the interesting question is, how can I get this to perform well? And what we looked into, well, the restriction we made is where we use tensor product elements, because in tensor products you have a structure. And that's actually an idea which is very old, like spectral elements have been doing this for 30 years or 40 years almost. Essentially, you just assume that your interpolation matrix has a Kronecker product structure. And when you do that, well, when you apply that, you can see that instead of writing out the Kronecker product as a big matrix, which gives you bad complexity and memory efficiency, you rewrite this as a kind of series of small matrix multiplication. You can interpret it physically. This is kind of just as a series of interpolation operations in 1D successively. And this gives you the right complexity. And then, of course, the question is, since this is kind of a series of small matrix multiplications, you could think, well, this is BLAS. So we just use a performance library, and we're fine. And here's the blue line is what our implementation is doing with kind of an Intel CPU. And the green line is what one of the most optimized BLAS implementation is doing as a function of the polynomial degree. And the problem for us is that the matrix sizes are so small that they are not in the optimal range of BLAS 3. So, well, we have lost because I have a big range here. It looks like on the right I win. The problem is high order finite elements, if you have fifth order polynomials, so it's quite far on the left, that's already very high order. The measures are not going to let you go much further to the right than 5. So that's really the range where we want to be. Now, of course, there's been an initiative which is batch BLAS, so kind of trying to have successive number of large or a number of more matrix multiplication. We did some projection on those methods, Essentially, the problem is that you don't really know what you put into caches, or on the GPU, it would be registers. And you lose on data locality again, and again, your memory limited on those operations. So again, you don't really win very much over the BLAS implementation here. Again, you could win on high order, but we don't go that high. And that's really, I want to focus on the own implementation. Now we did some kind of analysis and looking at what happens there. And the essential part is that we do the code locality. So we have a series of matrix-matrix multiplications, and we want to keep them in close temporal locality. So kind of really reuse the caches when we do the interpolations, when you do a quadrature point operations, and so on. And here we did some comparison of different methods. We even used like the blue line, which is our favorite one. You see on the right-hand side, this is the gigaflops. This is not the highest gigaflops number, because it's a different algorithm than the other ones, but it's the highest throughput on the left-hand side for the range that we're interested in. And that's really one thing I want to highlight is really, in the practice, gigaflops is only an interesting metric if you fix the algorithm. I'm very happy to change algorithms as much as I can to just reduce the work I have to do. So that's why I focus on the throughput number. We did one of the optimizations, just to give an example, is SIMD, which is of course important on CPUs. We have to have this kind of optimizations. We tried with auto-vectorization, which would be the yellow line here. Now I'm fixed the algorithm. Of course, now it's OK to do gigaflops. And you see, well, auto-vectorization is not very good. Well, it's OK for polynomial degree 7, because then you have blocks of 8 by 8 by 8. And that's a nice number for CPUs, because, well, you know why. However, it's much worse than when you do things manually. And the thing we prefer is the red or blue lines, which would be the vectorization across elements. So kind of an array of struct of array data type kind of data layout. But I don't know of a way to do this auto-vectorized by the compiler. So we really had to go to intrinsics, or of course we would want to be portable. So we wrapped this into a class which we call SIMD array or vectorized array. And you kind of have this code which is which depends on which instructions that you're compiling. Essentially, when I do SVE for ARM, I write 20 lines of code, and it could be applicable. Of course, now I want to test it on the real hardware, but it's essentially 20 lines of intrinsics that I have to add, and everything else just goes through it, because it's templated in C++ and it goes through. Of course, I pay a bit in compile time, but that's a price to pay. And now, of course, now just to give a perspective, this is again throughput, and the red and blue lines with the filled symbols, that's the matrix-free approaches. We compared them against the best matrix-based ones, which is the blue line and the blue one with the diamonds and the black line. And it's really the throughput that we are caring for, and you could gain in polynomial degree 4 or 5, which is maybe the highest you want to get in practice. That's up to an order of magnitude faster in throughput. So that's a nice result. So we really like these kind of algorithms. And you could, of course, see this when we do roofline. So just to show you how it happens. Now, on the lower right part, the black diamonds, that would be a matrix-based algorithm. It's essentially at the limit of the performance of the hardware. I mean, that's what I told you. It's quite easy to get to the performance limit with sparse matrix vector, because the performance limit is memory bandwidth. It's OK with matrix-free. Well, we started actually out quite to the right of the plot here, and then I tried to push it to the left again. So I reduced the operations because I used symmetries and all that stuff, because I don't gain very much if I get 20% higher gigaflops if I lose a factor of 2 in throughput. So that's really already after pushing it to the left. And you see we're pretty close to the limits. There's a bit of a factor in between, but if you're on the rich part of the roofline plot, then you know how difficult it is to get the optimal performance. So you could say that, well, even though now we skip this one here, so I could say that, well, matrix-free is really something which is faster than the best matrix-based methods by a big integer factor. And the improvement is because I go away from a memory-limited algorithm to something where I can compute more. That's kind of what the hardware is delivering me. However, even though I've spent many years on this project, we're still far away from the performance limits than we are in the other one. So, of course, then we cannot afford tuning for every single application. So that's something we need to synchronize, kind of get synergies from different applications. So that's why I do it in the math library deal too. And then we can just concentrate Navier-Stokes into what Navier-Stokes is about and not what about the implementation is about. OK. And kind of the things that we're doing here, this is just a code example here, how we write it. Essentially, the important part is the red cross here. That's kind of where you specify the physics. Now, the syntax, that's something I'm not the best person how you call the things, but essentially, this is Laplace operator. Essentially, you write one line that you test by a gradient and you have the gradient of your solution that you get in here, and you have it at quadrature point level. That's kind of what you want to write. Everything else is kind of standard. You can hide it. So this is the low-level interface that the ReL2 library gives you, which is already pretty short. And then you can abstract away everything else from the red bar if you kind of have a standard interface. And this is actually something which looks similar in the CPU and GPU. Now this would be just, again, when you abstract it away, the CPU code would be above here. And for the GPU, you write the upper part as a kind of a freestanding function, a kernel, a device function, which is just one. And then in a GPU, it's automatically then parallelized over the quadrature points because that's where you put the warps of the GPU. So that's essentially if you have this model, it comes almost for free. Of course, we need to replace the names because the evaluators have a different type, but that's something you can do with type def. So it's pretty okay for our purpose to do. Finally, we applied this in solvers. So this is a multigrid. So that's, of course, what you need to do when you solve linear systems. So multigrid is good for Poisson-type equations. We can even do adaptivity. We can do P multigrid, H multigrid. There's a lot of things you can do with multigrid. What is interesting now, this is a comparison between GPU, CPU, and Xeon Phi. So throughput on the left-hand side of a single node. What is typical of the CPU is they always have a bump here in between the middle. That's kind of when you can run most of the things from a cache. This is now a single node on the left. On the right, you see the multi-node case. The bump is gone on the CPU. And essentially, so there is a bump on CPUs, but you cannot utilize this on a large scale because this is where the communication latency hits you. So you don't see it in practice. So it's actually the GPU, the green line on the left-hand side, which is the most favorable architecture for this kind of algorithms. And just again, if you don't trust these figures, I mean, this is something I like here. The red lines, this is solving a Poisson equation with multigrid. The black circle here you have is one single matrix vector product with a sparse matrix. Just showing you again that sparse matrices is not the format you want to do in modern architectures. So we can solve a system quicker than matrix vector product. Of course, you can scale multigrid to large systems. So this would be continuous element on the SuperMUC NG. So this is a CPU-based machine. We have in Munich, that's the largest system in Germany. We have, and you see that, well, essentially you scale up to some limit where you have the latency, communication latency. You can do the same for DG. So this is DG now with a nice algorithm. Again, you see that, well, this is okay. If we look at the performance now, SuperMUC NG, this is a 25 petaflop machine in terms of peak performance. Lindbeck is around 19 petaflops, and we get 5 or something. Of course, this is cheating a bit because we use mixed precision where we can, so it's actually double precision would be only 3, but for being a PDE solver, which is memory bandwidth limited in the sense that you see that we actually realize a big fraction of the memory bandwidth. You could get around 210 gigabytes, so if you go to the definition of the efficiency, memory efficiency, that would be around 90%, so that's, or 85 to 90%. That's a nice number, given that this is a complicated algorithm. Finally, something we observed is now for simpler solvers like Helmholtz solvers, and something where we interact very closely with the US exascale initiatives on discretizations, is that when you look at benchmarks on CPUs, what you realize is that nowadays we've spent a lot of work on optimizing matrix vector products, so the green part of the plot. When you look at the conjugate gradient with a diagonal preconditioner, one of the simplest algorithms, and it's actually useful in fluid dynamics for Helmholtz equations, that's the precondition you typically choose, diagonal of the matrix. You see that it's no longer dominating the matrix vector product. You see that what is dominating is something that everyone assumes is free, the vector updates. The orange part, it's vector updates that everyone sees, well, it's scalable. There is no communication, it's nothing, but it's memory bandwidth. Of course, when you run in the middle region, when you can run from cache, you don't see this at all. But if you go to large sizes, which is many people are interested in, that's really hurting you. And what we thought about, well, how can we optimize this? And this would be going from the blue line here on the left-hand side to the red line. So this is both the Intel Skylake dual socket machine. And we optimize this conjugate gradient method. So we really go into the conjugate gradient. We look at what of the vector updates can we schedule next to the matrix vector product. So essentially, we use temporal locality of the data. Matrix vector product accesses some data. We do some things before and after that. So we kind of have one synchronization point per CG iteration, which is all reduced. We cannot go around that unless we do S-step conjugate gradients. But really go into that. And what you see is that, well, all of a sudden now, a Skylake can compete with a Volta GPU, where Volta has 3.5 times the memory bandwidth, and we're memory bandwidth limited. So that's a very surprising result. And the reason why we do this, well, it's actually an optimized version of CG, so we really do more work on this Skylake. But of course, the memory access, like Volta runs at 700 gigabytes per second on the baseline code. Skylake runs at 200 gigabytes per second because that's the hardware limit. We cannot go around that, but we are smart in doing the caching. Two things I want to say is that we try to optimize conjugate gradients. We could also apply parts of that to Volta. Not everything, because Volta does not have big caches, so we can only do some of the algorithms. But when you do that, the Volta is around 4, so it's around the limit of my plot here. So you could get more efficient also on GPUs by learning from that. And the other thing is, that's kind of my last sentence here, is that when we try to push the CPU, we can push the CPU pretty far because it has caches and allows it to do very nice strategies. But the code complexity, it's actually worse than programming a GPU. So I would just state, because we had what is sustainable and how much work is it to program on GPUs. If we want to use multi-core CPUs, it's at least as difficult as GPUs, because there is a lot of, now we try to use data locality. You need to break down all your loops that you can squeeze in vector operations in between them, which is, of course, like you don't write a loop in your code anymore, but you let a runtime or library schedule the loop, and in between it schedules whatever the vector updates are doing. So it's not nice from a code point of view, but of course that's the way we need to go. And just the final slide here, so this is something we did for CFD. Since I start with CFD application, I want to stop with that. So this is kind of a plot here, accuracy on the right-hand side, so error over the runtime that you spend. And this is normalized runtime to make different systems comparable here. And CFD is an area where many people have been investing money in. And you see that has been a benchmark, which is the orange dots here. So then there's different codes here on the right-hand side. And when you look at our results, we are in the lower left by an order of magnitude or more, which is a nice result, given that CFD is a mature field. But obviously, well, this is high-order CFD methods that they're using there. But I mean, it's really something that people have shied away from trying to optimize. And we really were able to show that you can do quite a lot if you know about the hardware. And that brings me to the end. So we really have efficient solver. And what we need to do is, like, we separate the finite element methods from the application code. And application code-wise, well, of course, there is the difficulty. Well, like everyone else, like we have to do a backend because there is not really a backend for us at this point in time. We're looking into Cocos and things, but that's not really the right abstraction for us. So we need to know about programming models. We need to know SIMD, CUDA, and so on. We do mixed precision, so mixed precision meaning double and single precision. We will need to invest into half precision in the future because that's where many hardware architectures are improving more. We need to have algorithms for doing that. We need programming models, so we have different backends, as I said, but we make the code look similar so you can replace one by the other pretty easily. And, well, the main thing, it's memory bottlenecks that we're seeing most of the time. So that's what I mostly work on eliminating. Thank you very much.
We have time for one question. We're kind of late. Okay, so if there is no questions, we will move on. And yes, thank you.
On va réduire la pause de un quart d'heure et on reprend à la demi.
Thank you.